Good afternoon, ladies and gentlemen. In this short video, I plan to go over the problems for practice A in chapter 17. It's problems 8 and 9 on page 626. All right, so we'll start with the first one. The first one says the magnitude of a uniform electric field between two plates is about 1.7 times 10 to the 6 newtons per coulomb. Newtons per coulomb. So you remember newtons from force per coulomb. If the distance between these two plates is 1.5 centimeters, find the potential difference between these plates. All right, so here's what I wrote down for this problem. They tell us the electric field strength, and that we use E, capital E, and that's 1.7 times 10 to the 6 newtons per coulomb. Here's my representation of two plates that can be two pieces of metal, can be whatever, some sort of conductors, and there's a space between them, 1.5 centimeters. And then I remember, newtons as kilogram meters per second square. I need metric. I'll go ahead and change that right now, which is equal to CN is 100, so that's 0.015 meters. Okay, 0.015 meters, that's what that is. And they want to know what the potential difference is. What's the potential difference? So potential difference is symbolized as change in V, V for voltage. So I direct you to this handy dandy review sheet that I made for you guys, and let's move this down. There's a little bit of here what is electric field strength. Okay, so there's something part of that. What that is, change in voltage, change in potential difference is the change in potential energy divided by Q, the electric charge. Okay, so we have here the change in voltage is actually potential difference, and it's equal to the magnitude of the electric field times the displacement. Okay, also change in voltage is the Coulomb constant and the charge divided by the distance. So this is the one that we have here. As here we have, write that down. I've got change in voltage is equal to negative E delta D. There we go. So we have the E and we have the D. Now, we kind of work on units to figure out why is that going to end up as in voltage. So let's plug this in. So I have here, and I'm just really interested in the magnitude. So I'm going to put in here E, 1.7 times 10 to the 6 newtons per coulomb. And I'm going to multiply that by 0.015 meters. Okay, using the calculator. There we go. 1.7 times 10 to the 6. There we go. Bring that down. Times 0.015. There we go. So I end up with 25,500 volts. That's what I end up with. And if you want to put that in scientific notation, 2.55 times 10 to the 4 volts. Okay. And if it's two significant figures, which we do have two significant figures, 2.6 times 10 to the 4th volts. Okay, now why is it volts? All right, so we have newtons per coulombs meters. So let's see here. Newton meter per coulomb. And hopefully, let's see if I turn off the light. Hopefully you remember that a Newton meter per coulomb, a Newton meter, hey, isn't that a joule? Yes, it is. I'll spell it out. Joule per coulomb. And I draw your attention to another handout that I posted. And I whipped this up for you guys. Just a sort of background on what electrical potential is. Kind of hard to show you since we're talking about electrons here moving around. And as you come down here, it says a volt, by definition, is joules per coulomb. Joules per coulomb. That's what a volt is by definition. And that's what we have here, a joule per coulomb. So there we have it. That is a volt. Okay. So this one is just using the equation on your on your summary sheet about the potential difference. Okay, all right. What is a potential difference? It's the change from one side to the other side. Okay, of the plates or whatever you're talking about. All right, let's go on to number 9. Let me see, I got to turn the page here. Number 9. Okay, number 9. Here it is. We have in the figure below, find the electrical potential at point P. So where's our point P? That's this guy right here. This point right there, due to the grouping of charges at the other corners of a rectangle. They just happen to form a rectangle. So we have a positively charged on this side, and we have a negative charge. The units here, negative 12 microcoulombs. This one's positive 8 microcoulombs. And on this side, we have negative 8 microcoulombs. So the question is, what is the electrical potential at this point right here? Okay, so come over here. I drew it out for us. All right, so here I draw your attention again to our handy dandy summary sheet. And here's our potential. We have Q, because they gave us the charges, and that's in Coulomb, and then times the Coulomb constant, and we have here the Coulomb constant, it's here somewhere. There it is, the Coulomb constant, 8.99 times 10 to the 9 Newton meters squared divided by Coulomb squared. So divided by R, the radius. So we have here, it's the Coulomb constant times the value of the point charge, and they gave us the values of the point charges in coulombs, divided by the distance. Okay, so we have 3 different charges, one here, one here, one here. So all I need to do is let me write down that equation. The change in V is equal to the constant, the Coulomb constant, times Q all over R. Okay, so that's what we want. There we go. That's all we need. So if I do it just for this one, ignore these 2 guys, and I just need the distance between that one, I can figure out what it would be due to this charge. I can do it for this one and also for this one. Then we can add them up and see what we have. So I'm going to go and fill it out. Between these 2 is 0.35. Okay, that's nice. Between these 2 is 0.2. So since it's a rectangle, between the point P and this 8 must also be 0.2 meters. And because these 2 are 0.35 meters, then clearly the distance between P and this positive 8 microcoulombs is also 0.35. So we're going to take each of these 3 points one at a time. All right, so let's do the first one. I'm going to write down what K is. We need to know what that is. 8.99 times 10 to the 9th. No, I don't have this one memorized. All over Coulomb squared. Or I could have just said Newton meters over Coulomb squared. Okay, so let's take the first one. The first one, we'll do this one that's just straight down below. So I'm going to say here, I'm going to call this delta V1 for the minus 8 microcoulomb. That's our first one. All right, so I want the constant times 8 microcoulomb divided by the distance, which is 0.2. Okay, so let's write that down. 8.99 times 10 to the 9th Newton. Oh, and this is Newton meters squared, sorry. Correct? A Newton meter squared, all over Coulomb squared. There we go, Newton squared. That's our first one. Now times Q. The Q is negative 8 microcoulombs. We don't want microcoulombs. We want coulombs. So remember that 1 micro whatever, meter, coulomb, whatever, is just 10 to the minus 6. So it's 1 millionth, okay? So this is 1, 2, 3, 4, 5, 6. I'll put here coulomb, could be meter, coulomb. There it is, 1 coulomb. All right, so we can go ahead and put that in there, times minus 8 times 10 to the minus 6 coulombs. All right, and divide that by R. And what is R? 0.2 meters. All that by 0.2 meters. So let's look at the units first. I always want to make sure I'm doing it right, check the units out. So one of my meters cancels out here, and one of my coulombs cancels out here. So I end up with Newton meters over coulombs. And like in the last problem, Newton meters is a joule. And by definition, a joule per coulomb is a volt. Okay, so I've got that right. Let's do the math. Plug it in here. All right, clear. 8.99 times 10 to the 9th. There we go. Times, okay, I got to remember it's negative. So I'm going to go ahead and write down here. This is negative. I got a negative number here. Negative times positive divided by positive. So it's going to be negative. Then I have to put it in here. Times 8 times 10 to the minus 6. There we go. And all that divided by 0.2. Nothing is squared. All right, divide all that by 0.2. Okay, so I get negative 359,600 volts. I'm just checking here is what I got here. Yep, 359,600 volts. And if you wanted to put that in scientific notation, I got 3.596 times 10 to the 5th. Okay, so that's my first one. That's the first one. Let's take the next one. Let's take, I want to call it change in voltage, second one, and we'll do it to this one because that's a straight shot. It's 0.35, and that one's the positive 8 microcoulombs. Let's do that one. So we're going to do it again. That one's equal to 8.99 times 10 to the 9th. I know that the units work, so this time I'm not going to do the units. All right, times, now I've got plus 8 times 10 to the negative 6 coulombs, or we're not doing units. Okay, all divided by, now I got the distance 0.35. The distance between P and that one is 0.35. All right, see what we got there? Okay, I'm going to do this again. 8.99 times 10 to the 9th. There we go. Times 8 times 10 to the 6th. Bring it down. So far, it's similar to the other one. Divided by, but this time we're divided by 0.35. 0.35. Okay. Whoa. Looks like, oh, look, I said, I didn't divide, huh? I said plus. Caramba. Try this again. 8.99. I'm having a problem here. 8.99 times 10 to the 9th times, oops, bring it down, times 8 times 10 to the negative 6. There we go. Bring that down. So I didn't do. Divided by 0.35. There we go. And there's my big number. I have 205. What is it? 205, 485.7143 volts. And if you wanted to do that in scientific notation, I have 2.055 times 10 to the 5th volts. Okay, that's my second one. Now I do the next one. What is it? What is the change for the 12, for the negative 12 microcoulombs? All right, so this is going to force you to remember your geometry. We need to know, I'm just going to try to draw a straight line. We need to know what this distance is right here. We need to know what that distance is. What is that distance? How do we do that distance? Well, hopefully you recognize a right triangle. There's a right triangle here, and there's a right triangle here. So either one you want to figure out, you know that the square of 0.35 plus the square of 0.2 is going to be equal to the square of this distance d. Okay, so let's figure out what d is. See if I can, right here. Yes, I'll do it over here on this side. D is equal to the square root of 0.35 squared plus 0.2 squared. And just as a review, a squared plus b squared is equal to c squared for a right triangle. So straightforward enough. Let's figure what that is. So I'm going to say, please give me the square root of 0.35 squared plus 0.2 squared. Okay, Just tell me what that is. And it tells me it's, oh, look at that. I made a mistake. I said 0.2 and I meant 0.02. And clear that. Try that again. Important to put the right thing in there. 0.35 squared plus 0.02. It is 0.2? It is 0.2. Sorry, you guys. It is 0.2 squared. Okay. So this time I got something different. So I don't think that's right either. I don't think there's a confusion between the answer one and the x, square root x here, this one right here. The x versus that one. So I think I hit the wrong one. Let's try it again. 0.35 squared plus 0.2 squared. Okay, there we go. 0.403. That is correct. 0.40311. 2887. All right. So here's what I'm going to do here. I want this to be as accurate as possible, and I want you guys to start learning how to do this with your calculator. So notice how here, oh, I rewrite this. Here we go. 8.99 times 10 to the 9th. And what is the next one? Q, which is the negative 12 micro. So negative 12 times 10 to the negative 6 coulombs. All divided by this whole long thing, this 0.403, 0.40311, etc. So what I'm going to do is I'm going to leave this in my calculator, and I'm going to take the inverse of that number. Let me unzoom here. I'm going to take the inverse of that number, so it's already there. I'm going to take the inverse, 1 over that. Give me that. Okay, so there it is. There's the inverse. Now I'm going to take that and multiply everything in the numerator. So I'm going to say times 8.99 times 10 to the 9th. Bring that down. Times, and what do I have here? This is the negative one, so I got to remember it's going to be a negative number. Times 12 times 10 to the negative 6. Okay, there we go. So that's more accurate than my, cutting this number down to 0.403. All right, so now I have 267,619.3433 volts. Okay, so now what you have to do is just take those three numbers and add them all up. Unfortunately, I cleared my calculator when I was doing this earlier. I just kept arrowing it down so I could go grab it from before. I didn't do that. I already cleared it out and I made those mistakes. Okay, so this was negative. So I'm going to go ahead and say times -1. All right, there we go. Now it's negative. Now I'm going to add it to this big number here, add it to, say, plus. And again, if it was already in your calculator, you just kind of arrow up to it. 20548.7143, not as accurate as if I had left it there. Looks like, did I make a mistake there? 205,485. Yeah, I think there's something missing there. How do I go back? 205,485. 485. There we go. 0.7143. And I got to subtract that to this one here. Minus 359,600. There we go. And I end up with negative 421,731. So the total change, I'm going to add up all these numbers, and I got negative 421,731.629 volts. And here's where I would finally reduce it down into significant figures. So this is equal to negative 4.22 times 10 to the 5 volts. There we go. Okay, so this kind of called superposition, where we had to take each of the charges in consideration and use this equation. For my highlighter here, use this equation for the change in potential is just the product of the Coulomb constant times the charge, which is in coulombs, divided by the distance. And that's it. All right. So see you next time. Oh, I do want to encourage you, please, to make sure you see the Crash Course Physics. Let's see the number. Which ones are they? Crash Course Physics, and it's 26 and 27. That'll really help because they also go through the Coulomb's law. All right. Let's see here. Chica. Can't get this to. So I will see you next time. All right. Adios.